everyone, thank you so much for coming to this video. So today we're going to be extending our definitions for trigonometric functions. So please review the lessons on when we were graphing sine, tan and cosine graphs, and also when we went through the definitions of those functions, as that will come into really handy for this video. So the learning objective for today is to be able to understand and use the definition of secant, cosecant and cotangent, or cosec, sec and cot, and also to be able to use the definition of arcsine, arcos and arctan, or just the inverse of sine, cos or tan. So let's get started. Okay, so if we start with the secant, cosecant and cotangent graphs, so cosec theta or cosecant, that's just the reciprocal of sine theta. So it's just equal to 1 over sine theta. So keep that in mind when we talk about when we want to graph it. So I've drawn the two graphs here side by side just so you can see how they relate to each other. So we have the blue graph being y equals sine x, and we have the red graph, which is y equals cosec x. So the first point here written is that the graph y equals cosec x, that's undefined at any point where sine x equals 0. So that makes sense, because if cosec theta is defined as 1 over sine theta, and whenever sine x is equal to 0, if you did 1 over 0, you can't do that. That means that's undefined. So that's why at any point where sine x equals 0, the graph would be undefined, and you would have asymptotes at those points, because whenever you approach them, the value would just get larger and larger, but it will never reach that point because it's undefined. So if you look at the graph here, sine x crosses the graph at 0, so that means that 0 is also an asymptote. So as you can see, this graph, if it continues like that, it would just never ever reach 0. And similarly at pi here, or 180 degrees, sine x does equal 0, but then if you do the cosec x graph, as you increase the values, this keeps getting larger, but it'll never reach pi. And same from the other, if it goes from the other direction, it'll just never reach pi. So then pi, this line here, that's also asymptote. And then the same for 2 pi, because if you do sine 2 pi, that would be equal to 0. So it's undefined at any points when sine x equals 0, and that's just the same as saying that it has asymptotes at points where x is equal to nx. So if you see, it's always at pi or 2 pi, and then the next one will just be pi. And that's because, if you remember, the distance between any two points in the sine x graph where it crosses the x-axis, that has difference of 180 or pi. So it'll just keep increasing at pi where it crosses the x-axis, so the asymptote would also be like that as well. So the next point is that the graph y equals cosec x has minimum points at y equals 1, or wherever sine x has a maximum. So if you think about it, let's say you had the maximum point of sine x is at 1. So if you see here, you have that as pi over 2. And then if you did 1 over 1, that's also the minimum of the graph. And that's because if you divide larger and larger values of sine x, so as sine x increases here, if you go to 0 or pi 2, whenever you divide something by larger and larger values, your whole value of the function would just decrease. Because whenever you do 1 over 3, that would be smaller than 1 over 2. So that's when, as you go from 0 to pi over 2, which is the maximum for the graph y equals sine x, as you go from 0 to pi over 2 for cosec x, that values will just decrease. So similarly, we have here that y equals cosec x also has maximum points at y equals -1. So that's because that is the minimum point for y equals sine x. So that means for cosec x, it would be a maximum point. So you just flip around your maximum and minimum for y equals sine x, cosec x, from when you have y equals sine x, because cosec x is just a reciprocal of sine x. So that's just an overview of how you draw the graph for cosec x. So now if we move on to for secant or sec x. So sec x or secant x, that's just a reciprocal of cos x. So that means sec x is just equal to 1 over cos x. So then I've drawn the graphs, two graphs here, side by side again, just so you can see how they compare to each other. So the first point about the graph y equals sec x is that it's undefined at any point where cos x is equal to 0. So that's at the points pi over 2 and 3 pi over 2 here, and that's the same reasoning as for the cosec graph, because whenever you do 1 over 0 you get an undefined value. So any points where you have cos x equals 0 at pi over 2 or 3 pi over 2, these ones are just your asymptotes again. So the way to get, because again you have the period of 360 degrees, the way you get that is if you just do x equals m pi plus pi over 2, and that should get you your values for your asymptotes. So so for example, if n equals 0 and you plug that in, you'll get pi over 2. Then if you do n equals 1, you get pi plus pi over 2, and that's just 3 pi over 2. If you continue to get that, you would get all your asymptotes. So your next point is it has minimum points at y equals 1. So that's just again, like the same reasoning as before, that your maximum minimum points are just switched around here because you have sec x is just a reciprocal of cos x. So wherever you have y equals 1 for y equals cos x, so it's 0 and at 2 pi, that is the same as where your y equals sec x graph would have a minimum point. And then again, your maximum points at y equals -1. So again, it's just flipped around. So whenever you have y equals -1, which is the minimum for y equals cos x, you would just flip that around, and that would be your maximums for your y equals sec x. And then you could just join, if you join all your points together, you would just have your graph for sec x. So that's just an overview of sec x graph. So just remember that's the reciprocal of the cos x. So sec x is equal to 1 over cos x. Now if we move on to the cotangent graph, or just cot x, so that's just the reciprocal of tan x. So cot x is just equal to 1 over tan x. So I've drawn the two graphs again here, with the blue one representing y equals cot x and the red representing y equals tan x. So here are the two main points you need to know when drawing the y equals cot x graph. So the first point is that it's undefined at any point where tan x is equal to 0. So that's just the same reasoning as before. If you ever do 1 over 0, you just get an undefined number, because you can't do that. So that means that whenever you have 0, so at 0, at pi, at 2, at 2 pi, those are your asymptotes. And they happen whenever x equals m pi. So if you have 0, that's 0. If n is 1, that's just pi. If n is 2, it's 2 pi. And then the second bit is that it crosses the x-axis at every point where the graph of tan x has an asymptote. So wherever these points for like pi over 2, it has an asymptote. If you that means it's because as you keep getting close to the asymptote, if you get close to pi over 2, your values for tan x becomes really large and they go towards infinity. And if you remember, if you do 1 over a really large number infinity, you'll get a number that's really close to 0. And then as you keep going into infinity, that would just be 0. So that means that your cot x graph will just cross the x-axis whenever you have an asymptote. So that's at pi over 2 and 3 pi over 2. And then that's just the points where at the coordinates m pi plus pi over 2 and 0. So for example, if n equals 0, that you'll get pi over 2. So 0 plus pi over 2. And then when you have n equals 1 here, for 3 pi over 2, that's just pi plus pi over 2. So just remember those two main points, and then you could just join your points together like as you would do a normal like tan graph, and then you would get y equals cot x. So it's just quite simple. It's just using the definitions of when if you do 1 over 0, you get an undefined number, and then when you do 1 over like infinity, a really large number, you'd get 0. So and if as long as you remember the tan x graph, and if you've forgotten the cot x graph, that's okay. And this is the same for sec or cosec. As long as you remember the other ones, cos, sine, and tan, using these definitions we've just been going through, the points we've gone through, you'll just be able to easily draw those reciprocal graphs. So yeah, so now we've completed this first learning objective. Let's try some questions. We have an exam question here, so I just put up here the definitions for each of the cot, cosec, and sec, just for your reference. So feel free to try the question out yourself. So we want to solve for values between 0 and 2 pi. The equation 2 cos theta is equal to 5. We want to give our answers to 3 significant figures. So the first thing we want to do is we can just rewrite cosec theta in terms of sine x using this definition here. So we would have 2 times 1 over sine x. That's just equal to 5. So then if we multiply sine x with both sides, we'll get 2 is equal to 5 sine x. Then if we divide 5 by both sides, we'll just get 2 over 5 is just equal to sine x. And then to work out x, you would just do x is equal to the inverse of sine 2 over 5. And then you could just plug that into your calculator and make sure that your calculator is in the radians mode, because they want it with pi, so that means they want it in radian form. So if you do that, you should get that x is equal to 0.412, or this, we can also call this theta because they do want theta. And then if we draw out the graph for what sine theta looks like, so if you remember, it would be something like this, with this being pi and this being 2 pi. So then if we have sine, the inverse of sine 2 over 5 is equal to 0.412. So for the values of 2.5, we have the values here and here, and we want to work out between 0 and 2 pi. So we've got one solution here, which is 0.412. And then to work out the last solution here, we just want to do pi minus 0.412, and that would just be equal to 2.73. So that's your answer to this question. It's not that difficult. The first thing is you just need to remember what the definition of cosec theta is, and that's just 1 over sine x or sine theta. So let's just call these all theta just to make it easier to more consistent with the question. But it's okay as long as you remember at the end. And then you just want to solve it like a normal trigonometry question. And then the last thing, because they've given you the range for which they want you to work out the values of the angle. So to do that, just make sure you draw out the graph and see where how many solutions there is, and then what those solutions would be. So that last step is really important, and many students would lose out on that extra mark. So just make sure you do draw out the graph, and then you'll be able to solve for all the values. So now let's move on to the arcsine, arccos, and arctan and their graphs. Okay, so moving on to the second learning objective. So I've laid out the 3 graphs here, and I will just walk you through all of them. So the definitions of what arcsine, arccos, and arctan is, they're all just the inverse of the other one, sine, cos, and tan. So arcsine, that's just equal to the inverse of sine. Arccos is just the inverse of cos, and then arctan is just the inverse of tan. So then remember from when we were doing inverse functions, to work out the inverse of, to work out what the graph would look like, what the inverse of the graph would look like, you just reflect your fx in the line y equals x, and then you should get your inverse. But you also need to remember that this only works if you have a one-to-one function where every value of y only corresponds to one value of x. But then if you remember, for all of these graphs, for all of the sine, cos, and tan graphs, they all are periodic, which means they repeat themselves. But that also means that for every like y value, so for every like 1 we had loads of different angles that equaled 1, and that's the same for all the 3 graphs. So that means that all 3 graphs, sine, cos, and tan, they're not one-to-one functions. So the only way we can work out what the inverse is and how to draw the inverse of each of these functions, we have to limit the domain of each of them. So if we go on to for arcsine, for the inverse of sine, what we want to do here, what they've done, so I've written out I've drawn the 2 graphs, with the blue being sine x and the red being arcsine x. So we want to limit the domain of sine x, so we've limited that to minus pi over 2 and pi over 2. And that's because if you were to continue from here, and let's say you were to continue it like down here, you'd have more like values. You'd have like these y values here equaling 2 x values, and you can't have that. That won't be a one-to-one function anymore. So that's why we have to limit it to between minus pi over 2 and pi over 2. So using the definition with ranges and domains of inverse and just the normal functions, you always remember that you switch the domain and the range. So then, because the domain of sine x is minus pi over 2 to pi over 2, that means that your range of arcsine x would just flip around. So that would be now be minus pi over 2 to pi over 2. And then your domain is just what your range of your sine x is. So that will just stay between 1 and minus 1, because sine x never goes above 1 and it never goes below minus 1. So your domain of arcsine x, that's just your range of sine x, that will just stay as minus 1 to 1. So now moving on, so that's what arcsine and sine x graphs look like against each other. So now if we move on to arccos, or the inverse of cos, so again, we have to limit the domain of cos x in order to have a one-to-one function to have the inverse. So to do that, we've restricted the domain to being between 0 and pi, like this. And that's because, let's say we were to go like below 0, for example, we would go like this. And that would mean that we would have like 2 values of x for each value of y. And again, you can't have that. It won't be a one-to-one function then. So we've limited the domain for cos x between 0 and pi. And that means that the range of our arccos, our inverse of cos, that would now be between 0 and pi. And then for our domain, again, that's just below -1 and 1, because your graph of cosec never goes above or below -1. So that means that you keep your, that means your domain of your arc cosec, that would just be between -1 and 1. So now moving on to inverse tan or arctan. So for this one, we've limited, let me zoom in a little bit to just make it a bit more clear. You need to limit the domain again for tan x, and we've limited it between -π/2 and π/2. And that means that's because, like, if you remember, it repeats in every 180 degrees. So if we went on to draw this graph, for every value of y, you would have another value of x. So you can't do that. So that's why we only have, we restricted the domain of tan x between -π/2 and π/2. So that means our range of inverse of tan is now -π/2 to π/2. And then for the domain of inverse tan, remember that for values of tan x, you can have all the way to infinity and all the way to -infinity. There's no limit to each of them. So that means because the range of tan x is unlimited, that means the domain of arctan x is also not limited, which means that you can have your, you can draw your arctan x for all values of x. So yeah, that's just an overview of the 3 definitions of inverse sine, inverse cos, and inverse tan. So now if we try a practice question just to make sure you fully understood everything. So we have an exam question here, so feel free to pause the video and try it out for yourself. So we want to find the value of sine of arcos 3/4. So the first step is we just want to try and work with what we have in the brackets, arcos 3/4. So to do that, we can just say that A is equal to arc cos 3/4. So that would mean that if we, because that's just equal to like the inverse of 3/4, if we cos both sides, then this would cancel down to just 3/4, and then we would have cos A is just equal to 3/4. So all we want to do is we want to find out what sine A is. And we can use that using what we know about right angle triangles and the function. So if we draw out right angle triangle here, and we label this as the angle A, then using like SOHCAHTOA, we know that cos is just the, is the adjacent over the hypotenuse. So this is the adjacent, so we just have 3 and then 4. So we can figure out what this side is using Pythagoras theorem. So we know that 4 squared would just be equal to 3 squared plus whatever this is. Let's label that as x. So plus x squared. So then we know that x is just equal to the square root of 4 squared minus 3 squared, which is just the square root of 16 minus 9, which is just equal to the square root of 7. So then we know that this is root 7. So then we can just work out what sine A is. So sine A is, using SO, it's just the opposite over the hypotenuse. So that's just equal to, the opposite is root 7, and our hypotenuse is 4. So it's just equal to 7/4. And that's basically our answer to the question, because we labelled A as arc cos 3/4. So that means that sine arc cos 3/4 is just equal to root 7/4. So it's not that complicated, as long as you realise that you can label whatever's in the bracket as like A, and then using the definitions of inverse sine, we can worked out what cos A is, and then we just did some normal trigonometry and Pythagoras rules to work out what sine A is. So that's everything. I hope you found this useful and you now understand the definition and can use secant, cosecant and cotangent and you can also know the definition of arcsine, arcos, arctan, and their graphs. So make sure you review this all carefully and do some practice questions just to make sure you fully understand everything. But thank you.